Hello, I'm Batuhan. Today I will present the semiconductor manufacturing process, covering the journey from a raw silicon ingot to the final package chip. The process begins with wafer manufacturing. Wafers are cut slice by slice from a silicon ingot using a diamond-coated saw. Since this generates considerable heat, a coolant flows constantly over the saw. Initially, the wafer is around 914 micrometers thick with a bumpy surface. Through sequential steps of edge rounding, lapping, and etching, we remove surface damage. Finally, chemical mechanical polishing, means CMP, is applied to make the surface virtually defect-free, reducing the final thickness to 725 micrometers. Next step is oxidation. This step creates a silicon dioxide layer on the wafer, which serves as an insulator to black leakage currents. The most common method is thermal oxidation performed at high temperatures of 800 to 1200 degrees Celsius. We use two types. Dry oxidation uses pure oxygen to grow a thin layer with excellent electronic properties, and wet oxidation, it uses oxygen and vapor, which growing the layer 5 to 10 times faster, though it is less dense than the dry method. Photolithography is the patterning process that transfers circuit designs from a mask to the photoresist on the wafer. First, a light-sensitive photoresist (PR) is evenly applied to the wafer. Then, using a stepper exposure process, UV lights projects to the design onto the PR. Finally, we develop the wafer. If using positive photoresist, exposed areas are removed. With negative photoresist, exposed areas remain. Then we move to etching. This process removes selected materials to achieve the IC design requirements. There are two categories. Wet etching uses chemical solutions, while dry etching uses reactive gases and ions. As shown in the profiles, etching can be anisotropic or isotropic. Anisotropic one is cutting straight down, while isotropic one is creating curved undercuts. Now we impart electrical properties. Deposition coats thin films onto the wafer to create insulating or conductive layers. Ion implementation then turns the silicon into a semiconductor by implanting impurity ions. Implanting group 15 elements like phosphorus creates an N-type semiconductor, while group 13 elements like boron creates a P-type semiconductor. And next part is metal wiring. To connect the transistors, we use metal wiring. Aluminum is commonly used for these interconnections because it adheres well to the oxide layers. However, aluminum and silicon tend to mix at junctions, which can cause fracturing. To prevent this, we deposit a burial metal between them to ensure the reliability of the junctions. The final phase is packaging, completed in 4 steps. First, in wafer cutting, the wafer is diced into discrete chips along scribe lines using a diamond saw or laser. Second, in die attach, the chip is mounted onto a lead frame to transmit electrical signals. Third, for interconnection, we use either wire bonding with thin wires or flip chip packaging. Flip chip uses ball-shaped bumps, offering lower resistance and faster speed than wire bonding. Finally, in molding, the chip is sealed with chemical resin to protect it from heat and humidity. All of this completes the overview of the semiconductor manufacturing process. Thank you for watching.